So, Kat, I think you said that you were still confused about the model. Like, you understand the code part, or, oh, no.
Yeah, I mean, I like kind of understand the code part enough to follow along, but I still don't really understand what test we're actually doing.
Oh, okay.
And why we would do it and when.
Yeah, so the general idea, so let's actually take a look. So now that I've read in dat and made the, oh no, I haven't read in dat. Okay, so I'm going to read in dat. I'm using reader, so it'll create a tibble. So each person gets his own RT. Now I could, each person gets their own RT in each condition, but there's actually 100 in each condition. That's what this next little bit is. It says for each person and condition, group those, and do a summary counting the number of items per person per condition. So I made up the data, so I happen to know that there's 100 observations per person per condition. We could go in and say, okay, per person and condition, compute a mean of the value in the RT column. I'm actually going to do that just to elaborate on this. So I just copied the code I had for this. Well, in fact, don't even need to copy it. I can say, in addition to counting, we're going to say value equals mean RT. So now, this is person 1's mean RT in condition A, and this is their mean RT in condition B. And if I were interested in knowing, is there a difference is there a condition effect on RT? This is sort of what we had originally in the multivariate case, where we had two observations per person, one in one condition, one in the other condition. And if we had the code from before, I don't expect nor really want you guys to type this out. I'm just going to do it quickly just to show you that we could pipe that to ggplot and say on the x-axis put condition, whoops, on the y-axis put value, and group by ID, geom point, geom line. So this is the data. Each line is a person. And the dots reflect their means in the two conditions. So we might be interested, is there sort of an overall effect? Now, if we didn't have the lines there, knowing which people are from what, these dots generally, sort of the two distributions of dots generally overlap with one another, so it would be we'd be hard pressed to assert that there's a difference. But we do have the lines. We do know that this person is the same as this person. So we could go through and just compute a difference score. So what is this slope? What is this slope? All the slopes. Just eyeballing that all those slopes are positive. So a t-test will probably come out. If we were to just do a inference on the difference between the two conditions, that would probably come out as having 0 is not very credible. But this actually isn't the data that we have. We actually have, for this person in this condition, a whole bunch of RTs, and for this person in this condition, same person in the other condition, a whole bunch of RTs. And that measurement noise actually can be useful to add into our model. So we're creating a model that doesn't expect us to compute the mean for each person in each condition ahead of time. It's going to allow us to just give it all the raw data, and it will sort of figure out what the mean for each person in each condition sort of should be. Is that a little bit more straightforward? But we're still asking that same question: is do the means for each person in each condition reflect a difference that is non-zero?
So how is this still different than like a t-test?
It's not in the sense that it's asking the same question. It's just using all the data. It's not just using the means per person in a condition. It's using all the reaction times that around this dot. So this dot reflects a mean. There's probably a whole bunch of reaction times that are spread around. So it's taking into account measurement noise. It's allowing the model to know that how much it should trust each one of these dots as being sort of an accurate value.
Okay, so like I guess my question now, like, what is the actual name of the test we're doing right now? Like,
So this is
what?
It's a hierarchical model.
Okay.
So
like multi-level model. Like, what's the like?
Multi-level is another term
Okay.
for it. Mixed effects model is another term for it.
Okay.
There's technically slight differences in those, in like how you structure, like whether things are allowed to be correlated or not. We're doing the more general version, which is the full hierarchical model that allows where you're asking, okay, there's some mean amount of difference from condition 1 to condition 2 across the population, and there's some mean sort of intercept across the population, but we're also expressing, and there could be a correlation between those properties as they sort of arise from person to person.
I'm confused because when I think of hierarchical, I'm thinking of building a regression model where each block of variables is predicting one other variable, not just like comparing the means. Do you know what I mean?
No.
In the frequentist world?
Yeah, but building a regression model where
the blocks of you add in like certain
like hierarchical
variables at like, so you add in like one block of variables to predict an outcome,
Mm-hmm.
and then you add in another block of variables on top of that block to keep predicting that outcome, and then you can look at the unique predictability of like those sets of variables.
Okay, so that sounds a lot to me like ANCOVA, where you're using the residuals from the first block as the outcome that you're predicting. Like
no, you're still just predicting
the outcome.
The outcome.
But so is it then more
it's
like
basically the same as like your standard multiple regression, but you're adding the predictors in a sequence of steps.
Oh, okay, yeah, and
I think we're just getting confused with the term hierarchy.
yes, that.
And we're just like, wait, this is
yeah,
what we
okay. Then I guess that reflects my ignorance of the use of that term in that context. I would have sort of framed, because hierarchical, I mean, to me implies that there is like almost like a set relationship amongst things, such that one thing is a subset of another. So you could have each individual is like a subset of a group, whereas the I won't argue terminology and try to assert that one is better than another. I will just say that that sort of blocked stepwise regression that I think you are used to talking about hierarchical is completely different. It's a completely different thing. And had I known that was a thing, a term that was existed, I would have clarified. So apologies for my ignorance on that. So we will get into scenarios where you have sort of multivariate stuff, and I will say that the general concept of stepwise anything is fairly widely denigrated.
It's not stepwise regression.
Maybe I learned it differently.
Because there's different types of there's like a stepwise regression, and that's not what this is.
When I think of hierarchical, I think of stepwise.
There's actually a thing called like stepwise regression.
Yeah, and that's usually when you add in each predictor in a specific sequence, and you stop when you stop observing an improvement.
Right, and that's different than hierarchical, because in hierarchical, I think it is just based on your conceptual.
Yeah, I think of hierarchical as like you found this model previously in the literature that you know works, and now so you run that, see if
And
it
then
still
you
works,
add
and then you
stuff.
add stuff.
Yeah.
So you
Yeah.
But it's different than like stepwise. Like if you open Andy Field's textbook, he says this is stepwise regression. That's bad. Don't do it.
Yeah.
This is hierarchical regression.
Gotcha.
Do that.
Yeah.
So then, what is this again? Like
This
what?
is.
Like if I was to Google trying to figure out this test,
Yep.
what would I Google?
Well, it's a hierarchical model.
Okay.
With all of this, I mean, everything that sort of I'm teaching you. At the outset, I expressed that okay, that first scenario we talked about could be considered like a Z test, and then the second scenario could be considered like a T test.
Yeah.
We're getting into the world now where there's not like a named test for these. We are expressing models for the data and asking what are believable values for those models. So there's not like a named test. I know that SPSS has like a mixed effects model add-in that you can buy, or it might be built in.
Anyway, we haven't done multivariate stuff in SPSS, so that's
right. It depends on. Sometimes people consider hierarchical multivariate or not. I certainly consider it multivariate. So this is hierarchical models, mixed effects models, and multi-level models are the terms. There's technically a distinction between those three in that one is some set of the other. I know hierarchical is the superset, like it's the more general descriptor. So that's what we're trying to look at, and we're using the hierarchical structure, the idea that you've got a population of people, and you're trying to say, okay, that population of people has a mean difference score, and that population of people has a mean intercept, and you could have a correlation amongst those two things across the population. But then within each person, you have a whole bunch of observations in each of the condition that that person's intercept and difference score determines the means for. So that's why it's hierarchical, in that you've got a distribution expressing the sort of center and variability of the parameters, but then within each person, you then also have sort of a distribution of observations. With here, the variability is just determined by measurement error.
I don't know if this is going to make anything any clearer, but this is the definition I think that they're going on for hierarchical modeling.
Yeah, no,
which is.
Yeah, it's that. Yeah, it's.
Yeah.
I don't need for. I'll take a look at that later, but I can say for now it's very different. It's a very different thing.
Well, yeah, this is comparing means, taking into consideration, and yeah, that's fine. I just.
All right. So, with this data, where we've got it as individual observations per person in each of these conditions, we want to do some inference on it. So we need to create that contrast matrix that basically encodes condition as negative 0.5 and positive 0.5. And then before I'd had you guys doing that by hand, but as we get to more complicated models with more predictors, that will become laborious. So there's a trick to get the condition contrast matrix in R sort of automatically.
Condition contrast matrix.
Yeah. So this is for that just column that's negative 5 and positive 5.5.
Oh, okay.
Yeah. Because with more, so the next example is going to have a scenario not with just one predictor with two levels. It's going to have two predictors that could, and we're interested in whether each one has a main effect and also whether they have an interaction. So that ends up being a lot of columns that we have to add in, and I don't want you guys to bother doing that by yourselves. This is a way of automating the creation. So in this circumstance where we just have one predictor condition, it would be easy to make
Oh, sorry. Nope. Never
Yep.
mind. I found it.
Yeah. In this scenario where we've just got one condition, one predictor that has 2 levels, it would be easy to make these the contrast matrix, but this will do it automatically. So we have to do some things ahead of time. So convert condition to a factor, and make sure the default contrasts are these Helmert contrasts. I told you that's just another word for the intercept and difference way of thinking about things. And then we use the model matrix function. And all this thing here, the value we're supplying as to the argument, the object argument, is a formula describing sort of the relation. There's a squiggle that's saying on the left-hand side is the outcome, and on the right-hand side is the predictor. We just have one outcome, RT, and one predictor, condition. So we can run this bit, and that gives us out our model matrix. It automatically adds a column for the intercept, and that's good because that's what our stand model sort of is assuming is coming in, is a matrix that has a column for the intercept. And we have a column for labeling what's in the condition column. Now I had you guys doing negative 0.5 and positive 0.5 before. Model matrix automatically puts negative 1 and 1. That won't be an issue though, because I have a different function that will automatically get the predictions on the proper scale. So don't worry about that change from negative 0.5 to 0.5 to now being negative 1 to positive 1. So with our model matrix in hand, we've got all the sort of things that Stan wants. We can tell us how many observations there is in our data frame. We can tell it how many predictors we have in the model matrix. Tell it how many subjects we have. This was the trick to ask how many subjects there are in the ID column. We ask how many unique subjects there are. We give it a list indicating the subject that's associated with each column, with each observation. The trick to make sure that it's the sequence of numbers in that list, regardless of what you named each person, maybe it was sub 1, sub 2, etc., to get it to be the sequence of numbers 1 through the number of people you have, you turn it into a factor, and then you immediately turn it into a number. X is that model matrix that we created, and Y is the column of outcomes. And again, because we've created code inside the Stan file to scale this, we don't need to do any scaling in R here. So, can define that, and I'm going to pull that over. I think I had you guys change this to chains equals 4 and cores equals 4. That will run and sample.
Where do we find stan mod? Because it says object equals stan mod, but it says stan mod not found. So
At the very top, I had you on line 7 compile. So maybe that didn't.
Mine gave me an error saying error in module, comma, must start equals true, failed to initialize module pointer, error.
Whoa.
I have no idea what this is talking about.
Yeah. That sounds like something akin to what you had. Let me come see quick.
Well, I know R released an update, so I'm downloading the new update.
I updated it earlier
to
today.
3.31.
I wonder if, having updated, you need to go through those install instructions again.
Everything else worked.
Let's just quickly say install the packages. restart this. To save. Similar. Yes. It's restarting our session. Don't worry. No, don't save the workspace.
Takes so long to open my computer.
Okay. So when that's done running, you should be able to start from the top. Get all the way down. Sorry. That's the best.
I got this.
That's fine.
That's fine.
So I have it too, so. We're starting to get into complicated enough models that there's sometimes some warning messages. They kind of look like error messages. It had numerical problems, and it says something, and it says count. The last line, though, is important. If the number in the count column is small, do not ask about this message. So I've got a count of 12 here, count of 11, count of 9, and a count of 4. I asked for 2,000 samples. Meanwhile, these are all like 10, sort of in the 20 and under. So that's definitely a small count. If you had like half your samples, like if this were up to like 1,000, that would be bad. But if it's like 10% or less, the number of samples that you have, then you can ignore it.
Isn't it weird that, so when I run this now, like, and this happened last time too, I get this thing pop up in viewer and like I don't actually see all of this stuff that comes up.
That's because the way it does parallel chains on PC is slightly different from how it does it on Mac.
Okay. Do you get that too?
Yeah.
I just don't get like anything.
Yeah,
It just was like click refresh button to see the progress, and if I do that, then that stuff comes up. But
Mhm.
if I don't get anything.
Yeah.
And it still looks a bit different.
So we can. How's it coming?
Oh, it's compiling the model.
Yeah.
Now.
Oh, okay.
Well, pre-compiling.
Yeah. Okay, so if we look at our output, it's a lot bigger than all our previous models. That's because it's actually giving us output for every subject, what a posterior on that subject's intercept and difference is. Critically, looking at the effective sample size and the R-hat column, they're all 1 and above 4,000, so that's great. If we wanted to look at the correlation between the intercept and difference, that's in the row section. That row section is describing a matrix, so it's saying the first column, first row, that's going to be just all ones. Ditto the second column, second row is all ones. It's the off diagonal that we want to refer to for that correlation. Credible interval goes from 0.02 to 0.77, kind of indicating that there's a correlation there. It's probably positive. It's so broad that you wouldn't really want to make an assertion as to how strong the correlation is. If that were much smaller, you could start talking about the actual like size, strength of the correlation, but there's a correlation there and it's probably positive. We could look up here at the sigma, mu, and tau to look at the values for these parameters on the Z scale, but we have at the very bottom sigma unz. So this is talking about the size of measurement noise. That data we'd read in was sort of values in milliseconds. So saying that there's about 42 milliseconds of noise in measurement within each person. The overall mean across people was about 480 milliseconds. That's pretty consistent with typical RT data. The difference in condition A versus B was about 40 milliseconds. Credible interval on that goes from 2 milliseconds up to 42. Wait, this isn't the lower. What is it? Oh yes, sorry, not 2 milliseconds. From 34 to 42. That makes a lot more sense to me. And these last ones talk about how variable people are from one to another in their intercept. So the mean across people intercept is around 480, but that distribution of intercepts has a standard deviation of about 100. And similarly, the mean for the distribution of different scores for each person is around 40, but there's about 8 milliseconds of standard deviation associated with that distribution. And you can look at the actual credible intervals for those variability parameters. It's not super interesting. Usually most interesting is, well, what is the intercept? What is the mean for the effect? And maybe what is the correlation between those two things?
And so is this where you can add in, I guess because it's multivariate, you could potentially add in multiple things and see how they're all related together?
Yeah, so we had the example from the other day where we had an idea that there was verbal IQ and nonverbal IQ, and then we added some other thing like mean reaction time as something that we expected would be uncorrelated with the other two. That can be done here. I don't have an example of that, though. The next example I have is more in the, but yeah. So again, the context for this data was we had observations from lots of people in each of two conditions, but lots of observations in each of those two conditions per person. So we could actually estimate what the measurement noise was. With that, we can do inference in saying, okay, what is the difference between the two conditions overall? What is the overall sort of center point of the two conditions? And also, what is there sort of a correlation in between those two properties of a person's data, the center point and the difference? But also, what is the amount of measurement noise that we actually observe? So that's the sort of extension from the last scenario. Let's open up the hierarchical2.r. And I should say, Kat, how's the compile, and did reinstalling fix everything?
So far, so good.
Awesome. Before I move on to hierarchical 2, are there any sort of other questions about this scenario? Again, it's just like the earlier multivariate scenario where we had data from two conditions that we then sort of recharacterized as a different score and an intercept, and then did inference to say what is the mean different score and what is the mean intercept, and is there possibly a correlation between the two? Except that now we have lots of observations per condition, which allow us to not only observe those properties, mean intercept, mean difference score, and the possible correlation between them, but also what is the measurement error. Okay, so hierarchical 2 is the same sort of scenario where we've got multiple people, each of which measured multiple times in a set of conditions. This time, instead of just condition A and condition B, we've got A1, A2 as one variable, and B1, B2 as another variable.
So what are A1 and A2?
Let's say it's a scenario where you have people, they're both within subject manipulations, so under speed emphasis versus accuracy emphasis. Maybe that's one variable. Maybe that's A. The variable A1 is under speed emphasis, A2 is under accuracy emphasis. So you'd expect people to be faster in the A1 and slower in the A2. And B is maybe morning versus night. So B1 is morning and B2 is night.
So it'd be like a 2 by 2 with like 4 cells?
Yeah. Yep.
Are both of these the hierarchical one we just did in this one? They're within the first one?
Yep.
was within as well?
Yep, first one was within, because you've got an intercept per person and a different score per person. And now we just have a scenario where, to put it in sort of traditional ANOVA type terms, the first one was just a one-way ANOVA, one-way repeated measures ANOVA, with 2 levels of the variable that's repeated measures. This one's a 2 by 2 repeated measures ANOVA. And so we would be interested in the main effect of A, the main effect of B, and the interaction between A and B. Whatever A and B are. So maybe it's the speed, accuracy, instruction, and morning, night time. So let's read in the data, and that maybe it will be a little bit more straightforward. You don't actually need to recompile the model because it's already compiled. But we're going to run this. So we have 2 columns, A and B. I maybe should have called these like Q and Y or something, or Q and P, because we had the names of 2 conditions in the first example as A and B. Imagine this is a complete... Pardon me?
Isn't it using a different...
It's not. We're just... The nice thing about how I wrote the hierarchical.stan is that it will flexibly accommodate this new design. So the first thing was just a one-way repeated measures. The second thing is a 2 by 2 repeated measures. The way I wrote the hierarchical.stan, you could use either. It will be okay with both kinds of sort of experimental designs. So this is the same scenario as before, where we've got lots of observations. We can ask, so grouping using dplyr, grouping by person, condition A and condition B. What are the counts in each of those conditions? So person 1 in cell A1, B1, they have 100 observations. Person 1 in A1, B2 has 100 observations. A2, B1, 100 observations. So everybody has 100 observations in each of the 4 cells of the design. This is where that like model matrix stuff is going to come in handy, in that we still need to do some stuff to prepare. So we need to make sure that the A column is a factor and the B column is a factor. And we still need to make sure that the contrasts are set to Helmert as the contrast we'll use. But now, instead of having to hand create a new column that encodes this A thing as either negative 0.5 and 0.5, and the B thing as either negative 0.5 and 0.5, and then figure out how to code the column that corresponds to the interaction between A and B, this will just automatically create all 3 of those things. So I'm going to say head of MM so we can look at it afterwards. So this will, MM now, again, any of these model matrix will always have a first column with an intercept. We've got a column called A1 that has the numeric coding for the condition, what condition you are in A. You've got another column called B1 that encodes what condition you are in the column B. And you've got this column A1 colon B1, which encodes the interaction term.
Can you just repeat what like the reaction time until the A start?
Right.
What's
Yes.
to?
Okay. So
That's
this is saying
calculating
that
interaction?
sort of our model is going to want to predict reaction time as a function of A and B as predictors that can interact. That's what the times is. It's actually the same as A plus B plus A colon B. So A alone, that's main effect of A, main effect of B, and A colon B is a way of saying an interaction between A and B.
Okay.
The shorthand for writing this is just say A times B. A times B auto expands to A plus B plus A colon B.
So the long form story was A plus B plus A colon B.
Yeah, where A colon B, it means interaction between A and B. So having created that model matrix, we can just package everything the exact same way as we did before and sample the exact same way as we did before. I'm going to put this down to 4. You might want to put chains and cores to 4 as you had before.
Okay, so in the table up there, is it just A1 and B1
Yeah.
and we're not doing stuff with A2 and B2 yet? I'm very confused.
I am annoyed at myself so I created this data thinking, okay, I'll have these two things, A and B, and what are logical labels for these? Okay, well, I'll call it A1 and A2. Forgetting that when you do model matrix, it automatically takes the name of the column and puts a 1 next to it to create the name. But there's a level called A1, but that's completely unrelated to the name that's up here.
So what are A1 and B1 down there?
It's just the contrast for A, contrast for B, and the contrast for A interacting with B. You could ignore the ones there.
So the contrast for A is like, for example, for participant 1, their scores on A1 compared to their scores on A2?
Yep. So -1 is sort of the indicator that for that observation, for that person, it's -1 is A1 and 1 is A2.
What's A2?
A2 is just the name of the other condition.
Okay, so what can you...
I'm thinking of it as pre and post. It's
Yeah,
like
sure.
A1
Yep.
could
Pre
be
and post.
And A2 could be post.
Mhm. Yeah. I'm gonna.
Is it possible to
Can you have an example?
Yeah. I'm gonna change some things so that it's more straightforward. So say namesdat equals C. So ID. You have to put these in quotes. Sorry. ID, comma, pre-post, comma. I actually don't know if you can put a slash in there, so I'm going to put an underscore. What would be a good other repeated measures thing? So pre-post is one repeated measures thing.
They could do reaction time, pre-post, accuracy, pre-post.
Don't want to get into that because
No.
that's reaction time and accuracy are two outcome variables. Yeah. Now.
Training day. If you have, unless you're doing
Oh, well, you had time of
That's a
day,
measure.
morning, night.
Sure. Let's call it session.
So does it just know because the order we put them in that's the titles we're giving?
Yeah, so now if we look at at that, we've got new column names up here. Oh, I forgot to put the last column, which is RT.
So what's our what's our question in this experiment?
So I just realized that the header for the last column was left off. It needs to be ID, pre-post, session, and RT. And now we've got a header. Okay, so what is the question for this data set? So let's call A1 is pre and A2 is post. And B1 is, say, session, the first session, and B2 is the second session. So let's imagine we've got people coming in on each of 2 days. They do a test, they eat some food, they do a second test. So pre-post is about pre-food, post-food.
Okay.
Session is about which day they came in on.
Okay.
Maybe there's a difference between the days. Maybe the first day they eat high-protein food, and then the second day they eat high-calorie food. So session encodes like what
So
food
then-
they ate on the day.
Yeah, I was gonna say. So then session isn't the day really; it's the food.
Yeah,
type.
yeah, exactly. Yeah, sure.
Okay. And then
I thought the pre-post was the
Pre-post is, so pre is before food,
yeah.
post is after food.
session is one time to eat like fruit, one time to eat meat.
I'm gonna call this food.
And then so like A1 is pre, A2 is post.
Sure, yep,
B1 is the first food, B2 is the second food.
sure.
And then each person has, say, like 100 reaction time trials for each, like
Yes.
pre and post.
So there's 200 for each person.
Okay, it's polar.
Well, there's,
Well, I just made up a number there, but
yeah,
But like,
there's gonna be 400 for each person because each person actually comes in on 2 days,
right.
does a pre and post on each of those days, so
okay.
yeah.
And so what's our question? Oh,
So the question is there a change in RT from pre to post?
Uh-huh.
Is there a difference in RT depending on what food you were going to have that day? But most critically, there's probably is the interaction term is, does the change in RT from pre to post differ depending on what food you've eaten?
Okay.
Okay, so having done that, we can redo our, if we go back down to the trick to get condition matrix, we no longer have columns called A and B. We've got pre, post. So anywhere I see a $A, I'm going to put pre-post.
Wasn't it called A1 before? So
Uh,
why was it
A1
That was the
A1?
level within.
No, the whole problem was.
yeah, because the model
A1,
matrix.
B1.
So don't worry, that will you'll see that get fixed
No, but
next.
I'm just confused how we had A here because we always had that.
The model
Before
matrix.
was A1.
Yeah, it's because the model matrix takes the name of the variable and adds a 1 to it for some reason.
Oh, okay.
So
It
it's
really
like
it's to convey that that's a number now,
Yeah,
but
gotcha.
we happen to have something called A1 as a level of A,
I
so
thought it
that
just
was
was-
super confusing.
Yeah, I thought that like in the CSV file it was called A1
Ah.
and B1 and that's why we were getting those.
No,
Okay.
it was it's not because we had the labels A1 and A2.
We also
It was a screw up on my
For
part.
the counts, do we have to change AD to pre-post when you scroll up a bit?
If you wanted if you want this code to work later. So pre-post and food. I put food instead of session. To be clear. Oops. So that would make that work.
anywhere
Anyway.
from like anywhere after here, change A to whatever your pre-post thing is, B session.
So having made sure that both of those, the pre-post column is a factor and the food column is a factor, we can now write the model matrix. You'll have to write food times, or well, pre-post times food here.
If you call it food.
I call it food.
So now you can see that we've got a model matrix now with one column called intercept, another column called prepost 1. So it's clear now that what's happened here is the name that the model matrix puts at the top of each column is the name of the column, and then it adds a 1 at the end for some reason. We've got a prepost 1 column that encodes the levels of the original prepost column as either -1 or 1. We've got a food 1 column that does the same thing to the original food. And we've got a new column, prepost 1 : food 1, which encodes the interaction. So in our output, we'll get a posterior estimate for the mean for the prepost effect. That will establish, was there a change in RT from pre to post overall, ignoring what food type they were having. We'll have another parameter that encodes the main effect of food, regardless of pre or post. But we'll finally have a parameter that encodes to what degree did the pre-post effect change depending on what food they got, reflecting that interaction. So happily, we structured our stan file such that it actually can, it looks exactly as before. We package it up together the same as before, and we sample. It's going to take longer because it's a more complicated model that so if you think about it, there's 3 columns in that matrix, 3 predictors. There's the main effect of pre-post, main effect of food, and the pre-post by food interaction. We are doing a hierarchical model that is looking at not only the means for each of those effects across people, but also modeling a potential correlation for each of those effects across people. So with 3 effects, there's 3 correlations now, so it's a larger correlation matrix that it has to do inference on, and that's why it's starting to slow down, is because you have an expansion of that correlation matrix, and it has the computations it does just take longer.
Do you still get 1 intercept and 1 difference for it?
Well, no, you'll get 1 intercept, but you'll get a main effect of pre-post, a main effect of food, and an interaction between food and intercept, or food and prepost. Prepost by food interaction.
So, trying to wrap my head around what because the difference scores, it was the effect, but it was also like the physical difference between the means of the 2 conditions.
Yep.
So what would that interaction numbers be?
So imagine that eating, let's say that the food was protein versus calories. So imagine protein makes you actually slow down in your reaction times, whereas calories make you speed up. Maybe there's some sort of metabolic process that has to go through with protein that means that your brain gets more sluggish, whereas calories can go directly to your brain and speed up. That would mean that you'd get a pre-post score that shows a slowdown in the one food condition and shows a speed up in the other food condition. So you could say one of them is going to be positive and the other one's going to be negative. So what is the difference? That interaction term encodes the difference of different scores. It's the slope between pre-post between the pre-post slope between the two food sessions different from one another.
So the difference of different scores? Is that
Yep.
Okay.
I think that.
Yeah.
So, and this is sort of standard univariate stuff where, actually, well, it's standard repeated measures univariate stuff where it's difference of differences. So we can print out sort of that posterior summary here. Let me expand it though.
It's just weird because you don't, like, on the frequentist world, you don't talk about, like, you just talk about is there an interaction usually, like, significant. Like, you don't really talk about, like,
Quantifying it
Yeah.
or,
Mhm.
yeah.
Well, I mean, an interaction actually is the same thing in the frequentist versus Bayesian world. It's a difference of differences.
we don't
So
talk
we're-
about it like that necessarily.
Well, I don't think that maybe you've been taught that way, but that's yeah. So we get a similar output as before. Unfortunately, it hasn't carried over the names that are in the model matrix. So mu1 is that intercept column. Mu2 is the pre-post column because it's the second column in the model matrix. Mu3 is the food effect, and mu4 is the interaction. So same as before, we've got sigma, mu, and tau all up above here. These are all on the standardized scale, so we could probably just ignore them. Well, first we look at our hats. They're all ones, and our effective sample size, they're all above 1,000, so we can look at everything inside here. We'll ignore the sigma, mu, and tau because we've got...
Yeah, mine's not.
Oh, okay.
So what would make them not be above 1,000? Like what?
If you had a really complicated model and too few... If you had a super complicated model and it had a hard time searching the parameter space properly.
Sarah, you have to say this. Tony, you just scared the crap out of Sarah.
Sorry, I didn't mean to disrupt your class this much.
No worries. That
That was unintended.
yeah. With very large, complicated models and therefore a large number of parameters, sometimes the algorithm that it's using to search the parameter space gets stuck. Yeah, exactly.
Okay,
Which just means that you have to ask for more iterations in the sample, which is there's an argument to the sampling called iter, and you just put that to a bigger number than the default is 2,000.
What's that NAM?
Well, that's happening because it's in the row parameter, and remember that the row parameter is a correlation matrix. It's all ones on the diagonal, so 1, 1 is part of the diagonal, and you can't compute the r-hat for that. I don't know why it doesn't also have an NA for when you have another part of the diagonal, so 2, 2. Should be NA there. I think that's a quirk of just how it's computing those two numbers. Frankly, you should be ignoring the diagonal values because it should be 1.
How did you get your full table?
So I said print post.
Yeah, because when I did that,
Is your window big enough?
Yeah, but she only has like the head. Like kind of like when we print that head and we get like the first few lines.
Oh. Did you say head of post?
Oh, no, wait. It just gave me a small table at the bottom, like the big table, so I can't see the big table. I don't know why.
Oh.
So again, we can ignore the stuff, the sigma, mu, and tau, because we have unzed versions of those down at below. We would want to look at rho because those encode like the potential correlations. So rho 1, 2, that's correlation between the overall intercept and the main effect of session. The credible interval is these two columns. So it goes from negative 0.52 to 0.31. So 0 is still fairly credible as a value for the correlation between the overall intercept and the pre-post main effect. We could look at the correlation between the overall intercept and the main effect of food, and that also includes 0 in its credible interval. I think they all do. Like if I could just scan down through and look for ones that seem to exclude. So all the correlations include 0 in their credible interval. So there doesn't seem to be any strong correlations in the data amongst the effects we're interested in. So intercept, main effect of pre-post, main effect of food, and the interaction. We actually get for each person an estimate for that person's intercept, that person's pre-post difference score, that person's food difference score, and that person's interaction term, the difference of differences. So we get that for all the people, so big long list here. But critically, we've got the section down here, the unzeds. So sigma, as previously, is just an error, a sort of measure of measurement error. It's around 40 this time, similar to last time, because I kind of reused the data. Mu unz is, again, all those main effects of our model. So the first one is the intercept, around 519. The second one is the main effect, the pre-post main effect. So there is about an 80 millisecond difference between pre and post overall. The third one is the food main effect. So there's about a 60 millisecond difference between the two food conditions. And the last one is the interaction. So there's about a 9 millisecond interaction. So that is a difference of differences. So one difference was 9 milliseconds smaller than the other difference.
In the SPSS frequencies, to figure out which one was higher, you then compute a mean. So do you compute a mean?
Yeah,
after
I've got a nice little way to do this next. Critically, let's actually look at the credible intervals for these things. So the credible interval for the interaction excludes 0. So 0 isn't very credible for the interaction. Ditto the main effect of food and the main effect of pre-post. So all the sort of effects we were interested in, 0 is not very credible as a value. So let's actually try to visualize each of the conditions. I have created, there's some code below, starting 67, but you can look in the table of contents here. Visualize the location parameters. So mu is that location parameter. It's the mean of the population location as contrasting with tau, which is the variability of one person to another, which we're not going to bother with. So to get the actual samples that these summary statistics describe, so you've got these summary statistics here, to actually get the samples, you use the extract function from the rstan package. You give it the thing that contains your posterior samples, so that's the post object that comes out of sampling. And you also give it the name of a parameter that you want. You also have to put this square bracket 1, close square bracket. I find that a little bit annoying. But that gets you this thing called mu, and it's already a mu is what you get out is a matrix, str mu. It's just a matrix, so I want to turn that into a data frame. So the matrix sort of notation here means that it's got 4 columns and 4,000 rows. So each column is a parameter, and 4,000 rows is the 4,000 posterior samples we have for each of those parameters. So by turning it into a data frame, I can then, if I say head of mu, it just has these annoying x1, x2, x3, x4 labels for those columns. But I still have that thing called mm. if I say head of MM, it has the nice labels: intercept, prepost, food, prepost colon food, indicating it's an interaction. So I can just grab the names from MM and tell the names of mu to be those names. So that's what line 70 is doing. It's saying grab the names from the model matrix MM and apply them so that the columns in mu are a little bit more informative. So if I look at the head of mu now, they're just more informative. They tell me as the reader what is in those columns.
How do we know which, like, when to have some of them with a square bracket one and some of them?
So I happen to know that MM is a model matrix, and it has 2 dimensions in its names. So one dimension names the rows, the other dimension names the columns.
Okay.
So I need the second dimension, the names from the second dimension. Yeah.
So you would, if you looked up in the help, is that how you could figure out what you're writing it yourself?
Yeah. I kind of had to figure this out myself as somebody with lots of experience with R.
Yeah.
It would have been hard for you guys to do that.
Okay.
Yeah, which is one of the reasons why I just put it instead of...
Yeah. Okay, no worries.
So having this thing now called mu with nice named columns, we can actually get a visualization of what we had up here otherwise in the table of these credible intervals. Maybe we just want a nice picture. So that's what this next sort of section does. It's using the dplyr sort of workflow of things. So we're using the pipes. We're saying start with mu, pipe it to the gather function from tidyr, which is going to reshape it from its current, it says reshape to wide. It should say reshape to long, because it's currently wide. There's currently a bunch of columns. We want it to be just 2 columns. One column encoding what parameter we're talking about, another column encoding the value for that parameter. So if I actually just run this without grabbing the next pipe, it will just show you on screen what that's going to look like. So just 2 columns, one column that says parameter, the other column has the values that are in there.
Mine didn't show me anything.
Because you probably just ran the whole thing, yes? Or I just selected from here to there.
Oh, without the pipe.
Without the pipe, yeah. You'll probably have to like hit Command C.
Error function could not find it. Did you run the ones above it?
So you ran from 68 where it says mu equals, and then keep running, and you're still getting an error?
Oh, okay, I reran and it worked.
Okay.
But I did it before.
So once we've reshaped the long, is this even necessary? Sure, factor levels are in order. Well, this little bit just makes sure that the order of the par column is going to be those same names. So intercept, then main effect of prepost, then main effect of food, then the interaction. It might have ordered them alphabetically otherwise, and that would visually just look weird. Then for each of those parameters, we compute the median, the 95% or credible interval, and then also the 50% credible interval. And finally, we pipe it to a ggplot sort of flow. That eventually produces a plot that looks kind of like this. Where what I've done here is I've actually put the I've put the value on the x-axis and the parameter on the y-axis. I like that because usually the parameter names are kind of long to read, and it's a little bit nicer to just read them left to right, and then once you hit the end, you're looking at what the value of the data is. So intercept, of course, is going to be a really high value. Sometimes with these plots, you actually just omit the intercept, in which case it would narrow down to the sort of scale of the effects that you're talking about. I was being lazy, so I left it on. So this shows that here's our main effect for pre-post, our credible interval on it, our credible interval on the main effect of food, and the credible interval on the interaction. It's really small, so you can't really even see it very well. So I maybe wouldn't bother showing this visualization. I'd sort of just rely on the verbal description of the credible intervals of each of them.
Do you mind showing where you would cut out, like I'm just trying to figure out where in here you would cut out if you didn't want to show intercept?
What would I do? I think I do it right before even mu. So right before the pipe.
Okay.
I'd say mu equals mu such that mu pars, or what's it called? Oh, I wouldn't. Actually, it's just the first. I'd need to tell it to get rid of the first column. So I'd say mu. You know what? The best way to do it would be right before you reshape. Use the dplyr select negative and in quotes intercept and pipe.
So
remember
the extra bracket in the intercept quote there?
I do. So that's the name of the intercept column. Select is saying grab the columns, but negative this means toss that column. Think that'll do it? Nope. Damn it.
Why do you need a bracket around the
Like
it's
shit.
We're adding it in.
No. The fact that it has a parenthesis in the name is screwing it up.
Right of the shape.
Is it possible to just like not extract it? Or is that too complicated?
Oh god.
And you can't just say mu is everything but row 1. Like
Yeah,
set
you
mu
can. That I was trying to do it like a so. The better way to do it, I guess, is, or the one that's going to work, is to do it before even the piping. I wanted to avoid doing this because it is showing you something a little bit new, which is to subset a variable by using the square brackets. We want to keep all the rows of mu, so what goes inside the square brackets is what you want to keep in terms of rows and columns. On the left-hand side of the comma is what you want to keep in terms of the rows, and on the right-hand side is what you want to keep in terms of the columns. If you want to keep all of one of those things, you just leave it blank. So we want to keep all the rows. We just want to toss some columns. And we don't want the first column, so I think we could just do -1 there. I think. Remember, this is before, so this is when mu is still wide. I'm going to take a look at head of mu, and indeed that has gotten rid of the first column.
Sorry, so what?
So
why
this-
is writing just -1?
Because we don't want, so here, let me actually show you, if we run to just here and say head of mu, we've got 1, 2, 3, 4 columns.
Mhm.
I want to get rid of this first column because when we eventually did our visualization, the scale that the graph has to have to show this one means that these ones are really tiny.
Okay.
So I don't want to have this row in my graph. So I need to get rid of the data in mu corresponding to the intercept.
Okay.
So before I do any of this stuff, it's still in this wide data format, which actually is nice because I can just refer to the column number that it is in. I happen to know it's the first column. So what this little bit does is it says take off the first column of mu. -1 means
Okay. So if that was -2, it would take out the pre-post column.
Yeah.
Okay, gotcha.
Something happened that shouldn't have.
After names.
I think I know.
Right?
Another line. Yeah.
But it's just
And
there.
do mu equals.
So
mu
now-
Square bracket, comma, -1.
Turns out when I updated Sierra, I straight up deleted Xcode off my computer. So
Yes,
now I
yes,
have
it
to
would
reinstall,
have. Yeah.
reinstall Xcode and do all that stuff.
Yeah.
Which means that it's
No,
going
that
to
must
take
be
forever.
Oh, yeah.
So I'm just
Yeah.
waiting.
Because before the comma would be if you want to. You don't want to.
No, I know that.
No, I'm just telling you why.
Something gone awry?
Yeah. So it's like rough column.
Yeah, really.
So if you wanted to get rid
So-
of where did this?
Why are you down here? Yeah, you want to be up here.
Okay, so
Up, up.
I don't even know what's
Up, up, up.
happening right now.
so we made that first.
Hierarchical T.R.
So like
Okay,
we're
so
getting
start
rid of
up here.
this column.
Yeah.
So that on our graph,
And
so that our graph will look better.
Because on the
-1.
first graph it was so big that
Okay,
it made the scale
next
too big to look at
one,
the
yeah.
other ones.
Do that before. So do the names part
Okay,
before the
because this
-1.
Because it's all the way over here, it makes those
Oh,
like
okay.
super tiny, so you
Got
can't really
So
tell what's going on.
you'll have to start by
So
doing the
instead,
extract
we're gonna
first.
Just the intercept one. Right. And
Ooh, I've got a
it's
minute.
row and then column.
Because Sarah,
So
I've
we leave row blank, so we don't want to get rid
so
of
yeah.
it.
See mine. I've got the names part before
Yeah. So
the.
you do minus first column. We want to get rid of this column for -2.
Okay.
And all that was doing was Christiane asked if we actually wanted to get rid of that intercept
That's because you
entry in the
have-
plot
Those quotes around it.
to make it so that we can actually see the scale of the effects. So the intercept really isn't like an interesting parameter of our model. It's the effects that are more interesting.
We're doing visualized.
Where you are? No, where you were, sorry.
So we still haven't done what Christine asked about asking no, not the, like about the getting the means or like.
Right.
Like you said figuring out which
Mhm.
was affected.
So yeah, all we've done so far.
Food as well somehow.
No, I called food session. I
Oh,
left
you're
it
missing.
because he changed it to food after.
Did you maybe do it twice?
I'm missing.
If you hit it twice, then the first time you re-changed it into one.
Yeah, or you've taken off the first column twice, so
Oh my
like
God.
that's okay. That's
How do I put it back in?
start back from the very top of extract. So mu
I'm guessing that's what happened. Like if you ran it twice, because we've
Yeah.
actually like altered the set now.
Where
Right?
is
I mean,
extract?
And
so
then if you
line
did the
68.
typing again, you like
68-ish. If you actually just go to right, start at the top of the visualize location parameters
Yeah.
section.
But isn't that going to run it a third time? And then
No,
it's gonna
no,
go
because
on
we're
the next
recreating
Well,
mu
that's
from
what you
scratch.
one? Okay.
That's what that first line does, is it creates mu from scratch. So all we've really done here is made a visual representation of the table that you would otherwise get out of just printing thing, because this is just the this table here. So, but maybe if you had like a big table and you didn't feel like a large number of effects, and you didn't feel like describing them all verbally in your results, you could just show a single table and refer to it, or sorry, a single graphic and refer to it. The next little section, if we go in our table of contents, there's visualize posteriors for conditions as the last section. This is the one that gets at Christian's question is like, what are the predictions, or what should we believe about the means per condition? Like another way of asking is, what were the means for each of the 4 conditions? So this, I made a little script to do this relatively automatically.
But we have to replace A and B in it.
Down here,
Yeah.
yes, just down here where we have A and B.
What's it again? Food
Food
close. B is food.
whatever you
Okay, so if
Oh,
you
and
run,
then here.
But what about further down in the visualize with ggplot x equals A?
Yep. Yeah, you'll want to x equals pre-post, b equals food.
What's the median for y? I'm confused.
Y equals
equals
med. It's the median of
Oh.
the. So we're actually going to be visualizing the models. What the model says would be credible values for each condition. So that distribution of credible values, we're just going to arbitrarily choose a sort of central descriptor, median.
So
We could use mean.
So it's the median of what?
Of the posterior samples for the model's sort of prediction for that condition. So in the same way that you can say for our simpler models where we just had sort of an intercept and a difference, the model is parameterized such that you're talking about the intercept value, so you have uncertainty about what you should believe about the intercept, and you have the difference value, so you're uncertain about what you should believe about the difference value. You get the sort of output from the Bayesian thing is a bunch of samples from the posterior for each of those parameters. So for each sample, what you can do is you can say, okay, grab the intercept sample and grab the difference sample, and given those two things, figure out what would condition A, the first condition be, what would the other condition be. So you then get a prediction for those two conditions, or like what you should believe about those two conditions. And repeating that for all the samples gives you a distribution across each sample. Really, it's like talking about the credible interval for the mean for a condition, or the confidence interval for the mean for the condition.
Could you comment on, I think I've missed, so when the table that we ran before this one that we're doing now, and it gave us the 95% credible interval. I thought that was fuck. Okay.
Yep.
Let's do it for
Okay.
the table.
It's working.
Ow. What did you mean to do just then?
You mean,
Oh, it was just a
got
fist bump, but
but you punched the table. Gotcha.
But so what the stuff that we just ran and that gave us the 95% credible interval, I thought that was giving us what would be credible values?
Yep, credible values for the effects, the things that we actually are interested in different.
So these are credible values on the
for
scale.
the means for the original means. So let me actually show it.
Sure. Yeah.
So I'll just run all the way to the bottom. So we get sort of what you almost would expect to see as like a graphic for the data that you obtained. You've got on one axis one variable, so pre-post, and on the other axis, the other sort of differentiating the colors is the other variable that you had, food.
So you can kind of because the interaction is only like 9.
Yeah.
Right. So that's when you see like you got a bomb on her screen. Like.
Yep.
What?
Yeah, you're.
Oh my god.
Yeah, that's our studio just literally crashing. So.
Awesome. I hope you saved before you ran it. Nope. Yep. I find it usually once you open it back up, it's still there. It's still there.
Yeah, they've done a good job at integrating
Didn't change it. Okay.
But yeah, so like.
So from this, you can kind of see, like, okay, there's an overall difference between the two colors. That's the main effect of B1 and B2. There's an overall positive slope between A1 and A2. So that's the main effect of pre-post. And these two slopes are just like a little bit different. And that reflects the interaction.
I thought for an interaction, usually the lines have to be crossed.
Nope, just non-parallel. Cross would be like the maximum possible interaction, but anything non-parallel is an interaction.
Because it's increasing more for B2 than both are increasing, but it's increasing more in conditions.
But I thought to reach significance.
Nope.
You had to cross.
Nope.
Because that's how it was with SPSS. But it's the cognitive model that looks at significance.
Yeah, but no, but that's
But
even
also
just
even in
separate. Like, so technically, if you were to go into each individual data point and say, okay, this is A1. If I subtract from A1 the main effect of pre-post and the main effect of food, and then also do that for each of the points. If you subtract out the main effects, you always get a cross. And that's really what an interaction is actually evaluating. But in the raw data, it doesn't need to be a cross. So maybe that's what you're remembering seeing from SPSS is after you've sort of taken out the main effects.
I don't know, because we never had to physically take anything out of this.
Yeah, but maybe it's doing that automatically is what I mean.
Even in SPSS, so like an interaction can be significant if it's not if it's not a cross. Like it's just the effect isn't the same in each condition.
Yeah, there's a difference in the different scores. The slopes differ. They don't need to be opposite sign.
Yeah, but usually in SPSS they still, even if they differed, it wasn't a significant difference unless they overlapped, crossed each other somewhat.
I'm not even thinking just SPSS. I'm just thinking when I learned stats.
Yeah. But you could have a straight line and a flat line, and that could still be significant.
Yeah.
Or even if one's super steep and one's going up, but it's that could
Maybe people just use the cross as an example.
Yeah, a cross is ultimate interaction.
So on this one though, besides visually looking at it and saying yes, they have somewhat different slopes, how do we know that they're significantly different?
Okay, we're not
which
using
is we're not taking it
but
frequent.
how do we know that's meaningful? Then?
Yes.
Because it doesn't look meaningful.
Credible interval didn't have
because
zero.
there's an explicit. It's just like when you have the output from SPSS and there's the pre-post times food interaction line with eventually a p-value at the end.
Yeah.
That's what this is.
So we can't tell by that other graph that there's a actually meaningful difference. We need to look at the other data we looked at first.
The credible interval on the interaction term is what you want to talk about if you want to really ask, are these non-parallel or not?
Right, okay.
So on the other one, the other graph, it's meaningful because it doesn't cross where 0 is.
Yeah, 0 is not very credible.
That makes sense to me. That's
Okay.
Looking at the other thing doesn't make sense to me because it doesn't look like it's going to be meaningful.
Right.
Because they're so
Yeah.
similar.
Okay.
I wanted to show you this because this is the way of sort of double checking what the which one is what these different scores mean. Food, okay, there's an effect, but which one is the bigger value? So usually also your readers kind of expect to see a graph kind of like this where it shows the individual conditions.
They'd be like, what difference?
Yeah.
But even saying there's an interaction, but it's not big. When we say meaningful,
so,
the credible interval doesn't go over 0. But is it really meaningful?
Yeah,
Is it really that big of a difference?
Clinical versus statistical significance.
Significance testing. So.
Yeah. So yeah.
Well, if you look at how much the interaction,
Main effects?
the main effects, how much they vary. The bottom one, is that the intercept? Or
No, I
That's
tossed out
pre
the
versus
intercept.
post.
Yeah.
Yeah.
These are all just the effects.
You look at how much that varies. It varies way more than even the size of the effect of the interaction.
Right.
It's tiny.
So we're saying, the interaction's not 0.
It's an
It's
effect,
not
but
big.
it's tiny. It's a who cares.
Well, if you were a clinician, you might say, who cares? If you're a basic scientist trying to understand if in reality there is this, that then you now have to generate sort of a neurological model for how that could happen, you do care. So,
It also depends on what you're measuring, too. If that were, I don't know, if this was drug testing somehow, it could be.
So that's all I had for today. Again, this is sort of this is analogous to a 2x2 repeated measures ANOVA type scenario. That's what hierarchical 2 is. Hierarchical 1 was just a one-way repeated measures ANOVA with a 2-level variable, a 2 by nothing repeated measures ANOVA. But explicitly in a context where the data is hierarchical, so you've got for each sort of combination of conditions, you've got a lot of observations per person, so allowing you to estimate what your measurement noise is. Now, estimating the measurement noise, so far I haven't really even bothered trying to demonstrate what the benefit of that is. It does end up meaning that you have greater statistical power, and it allows you to be more accurate in like your inference on the correlations. But no, I want to get on to other topics, but another domain in which it's very helpful is when you have data such that you have more than one. So person as a variable, we include person as sort of like a predictor. We're saying like each person differs from one person to another in the size of their food effect. So what that's kind of implying is that a person themselves is pretty consistent from one sort of time you test them to another in terms of how big a food effect they'll manifest, but there's variability from one person to another. So the very common thing in psychology is to have people as like a unit of observation, that we expect people to be consistent within themselves, but to vary from one person to another. You could have a different scenario where you have some other measured variable, so we measure which person each observation comes from. Maybe there's some other variable that's measurable that allows you to specify that that variable also has levels that are expected to be consistent with themselves, but vary widely. So the example I gave the other day was lexical data, where you have, say, people doing an lexical decision task. And we happen to know that words are pretty consistent within themselves. There's high variability from one word to another in terms of how fast people are able to detect that it's a real word. And that's actually really consistent from across one person to the next, that say the word bear will have sort of a mean RT, and the word antelope has a different mean RT. Those are going to be really consistent mean RTs from one person to another. So in the same way that the people will have a mean RT within themselves that's pretty consistent but variable from one person to another, the words as a unit of observations are going to be pretty consistent within themselves across people, but different from one another in terms of what that mean is. So one of the reasons why hierarchical models got introduced to psychology in general is because the linguistics community realized that they are the solution to this problem, where you have multiple sort of units of observation that you want to be able to combine, and mixed effects models hierarchical models generally allow you to express that there's these two units of observations that are sort of consistent within themselves, and that allows you to get sort of way bigger power, like really huge power increases, because you're taking into account something that otherwise, so the variability from one word to another is just being considered as noise in the context of just having subject as sort of a unit of observation like we've had so far. But if you're able to actually have the model express that, oh no, words have this consistency within themselves, but variability between each other as part of the structure of the model, that no longer is noise. It's seen as like something that it's modeling. So that means that your power goes way up. There's a bunch of other scenarios like you can have. So that's an example of crossed sort of units of observation. Another phrase for that for units of observation that is used that you might see is a random effect. So that's an example of crossed random effects. There's other scenarios where you have, like, in the same way that we've got people as units of observations plus some random measurement noise within a person, you can also have yet more levels of hierarchies. So if you're measuring people in this experiment in one province and then you do it in another province and a few other provinces, and you want to express that, okay, well, maybe provinces differ from one to another in their mean RT. This is a ridiculous example, but maybe you can think of some other sort of psychometric scenarios where there might be that consequence. You can actually model multiple people, each of which having multiple observations, but those multiple people form a population, and then there's this sort of meta-population of all the provinces that has this variability. So yeah, it's really powerful. It also happens, we're not going to touch on it, but it also happens to be sort of a solution to the issue of multiple comparisons. So far we've only ever had like a comparison of two conditions in our thing. You can actually express that the magnitude of effects across your potential comparisons itself forms sort of a distribution. So you almost treat the effect as a unit of observation, in which case that has some properties that solves the multiple comparisons issue pretty elegantly. We won't go into that, though. But there are some nice benefits of hierarchical. I wanted to make sure that you guys were exposed to it before we go on to other scenarios of multivariate modeling where we don't bother with the measurement noise issue, or we don't include those aspects. So we're going to move on to other multivariate scenarios where we've got latent parameters and want to do inference on like the like structural equation modeling type. Okay, you've got sort of a intervening variable, and what is the amount of variance that's attributable to one versus another, that sort of thing. So that's where we're going next.
Can those be combined?
Yep. All this stuff can be combined.
Yeah.
Traditional frequent disk tools would not allow you to combine them, but you definitely can in R, because you just add the code to say this latent model plus now we've got a measurement index model. You add it at the end.
So yeah, I almost want to say it's